Hi, this is video I17. Oh my gosh. And last time we talked about estimating with finite sums, and what we were doing is we were approximating the area under a curve by breaking the area, that interval, into rectangles, taking some random y value in each interval and finding the areas of all the rectangles. And we're going to apply that idea to something that comes up all the time. What happens if you have a rate curve? So area under rate curves. And I'll show you what I mean by that. Let's say I have some random rate curve. Doesn't have to start at the origin. Just goes around like this. Okay, and this is a time, so t. And this is a rate. It can be any sort of rate. We'll start with a very simple one to build understanding. Let's say this is in miles per hour. And so time is in hours. Okay, so let's see what happens if we find the area under this curve by breaking it into rectangles. And I'm just going to randomly cut this up. So I cut it into 4. And it doesn't matter, but let's say I made them all equal. And let's take a right sum. And so in this interval, the right sum is an overestimate. In this interval, the right sum is an underestimate. And the reason that changes is because here we're increasing, and there, for the most part, we're decreasing. Here, the right sum looks like it's a little too high again, and too high again. Okay, but let's talk about what would happen if we found the area of one of these rectangles. Okay, the base is some sort of change in time. Maybe this is like we're 1 hour, 2 hours, 3 hours, 4 hours. So this is a change in time. The height is a speed. After 1 hour, how fast were we traveling? So let's say that this was 60 miles an hour. Okay, if you multiply that rate, which is the height of the rectangle, times this change in time, times 1 hour, and maybe a better way to write this, 60 miles per hour times 1 hour, you can see clearly the hours reduce and we get a distance, 60 miles, which would be approximately how far you would travel in the first hour. Okay, here, from this time to this time, the change in time is still 1 hour, different rate. Your velocity is still positive, and so you'd still be moving away, but at a lesser rate. Let's say this is 50 or 45. 45 times 1 would be 45. So in this second hour, you've gone approximately 45 miles. And so you can see that the area under this rate curve is a distance. But to generalize that, your rate doesn't have to be miles per hour. It can be any sort of rate. It could be water over a dam. Well, let's say it's gallons per second. And the time is seconds. If you multiply that base times the height, you'd get gallons in amount. So area under rate curves gives you some sort of amount related to that rate. And that allows us to answer questions like this. So question 1. A projectile is fired straight up. And its velocity is given to you with this formula. Okay, and let's say this is meters per second. How far does it travel? In the first 3 seconds. Okay, so this is our rate. If I were to graph that, this is clearly a line with a slope and a y-intercept. Okay, my y-intercept is 160. My slope is negative 9.8. And so it's going down. You could solve for v equal, or when v equals 0, you could find that that occurs after the time is 3, so I don't have to worry about going below the x-axis on this problem. Okay, and so here I have my rate curve, v of t and t. Okay, I'm going to now say I'm breaking this up, and let's break it up into 3 subintervals of equal length. Not very well drawn. Now, I'm going to use the idea of rectangles to approximate the area. Okay. Clearly, though, these are each trapezoid, so you could find the exact area. But let's go ahead and say that we were told to use a left sum for the approximation of the distance traveled. Okay, so what we would do for each interval, this is 1 second, 2 seconds, and 3 seconds. Okay, for each interval, I would take the leftmost point, okay, there for the second, and there for the third. This point is inconsequential. I would make a rectangle for each interval using the left point, and I would find the area of each rectangle. And I would say that's approximately how far I've gone in the first 3 seconds. So the distance. So I'll do that work over here. Get that boxed up. So the distance, and maybe I should record here that this is a left sum with 3 equal subintervals. So we're approximating the distance traveled. The distance is approximately these 3 velocities added up times the change in time, which is just 1. And so I have v of 0 plus v of 1 plus v of 2 times the change in the time, which is just 1 second. Okay, and so we can just really quickly clear all this out, enter this function. So I have negative 9.8x plus 160, and then I have to set my window, or set my table. I'm going to use the table function. I'm going to set it to auto, start at 0, and I find the 3 approximate velocities. 160 at x equals 0, 150.2 at x equals 1 or t equals 1, and 140.4 at t equals 2. All times that 1, which I'm going to ignore from now on. And then all I have to do is add them all up. And so let's see, that's 300.4, so 450.6 times 1. So the approximate distance traveled is approximately 450.6 meters. Okay, so then a question they would want you to be able to answer is this exact? Is it an overestimate? Is it an underestimate? And in this case, since we used a left sum with a decreasing function, we're adding too much because we added those, so this would be an overestimate. I think the correct answer is 435.9 meters traveled. So I think I'm going to stop there. You may be able to do 1, 2, or 3 on the review now, and I'll finish this section next time.